All right, so section 5.2 will introduce what we call the binomial probability distribution. Binomial probability distribution. And it has an interesting formula. So the formula is this: the probability of X successes in N trials, and I'll write all this down, is equal to N factorial divided by N minus X factorial times X factorial times the probability of success to the X times the probability of failure to the N minus X. Okay, so that's the formula. And we're going to use this many, many times, so we'll get pretty familiar with it. But let's describe what all these things are. So N is the number of trials X is the number of successes in those trials. And we're going to describe, we'll have to decide what we consider success and what we consider not success. P, little p here, is the probability of success. And little q is the probability of failure. And we tend to know P or Q. And because these are the only two possibilities in any of these trials, we have the requirement that P plus Q must equal 1. And from this, you can solve for any of the other. So oftentimes we're given oftentimes we're given P. So to solve for Q, most times we'll just take P and subtract it from 1. Okay, so in this problem, they want us to just identify these various letters. So let's take a look. So based on a survey, assume that 44% of consumers are comfortable having drones deliver their purchases. Suppose that we want to find the probability that when 6 consumers are randomly selected, exactly 3 of them are comfortable with delivery by drones. Identify N, X, P, and Q. So a percentage is a dead giveaway for either P or Q. And most of the time, it's going to be P. So our P here is, in decimal form, 0.44. Now we can get Q from this formula here. So we can say Q is 1 minus 0.44, which is 0.56. So there's half of the problem done already. And then also N and X, N is almost always the bigger number in the problem. So I'm only given 2 numbers, 6 and 3. So the number of people that we're interested in is 6, that's N. And then the number of people we want to say that, yes, they're comfortable with drones is 3. So X is 3. So that problem is just identifying the letters. We're not even using this formula yet, so it's not quite that difficult. Okay. I should mention also that this first part of the binomial formula, how do I want to do this? This first chunk here, that you might recall is just the number of combinations. So we called that NCR, or in this case, NCX. So this is the combination formula that we saw last chapter. And there's a button on your calculator. So you can shortcut all of this work by just typing, in this case, you would type 6, and then NCR button on your calculator, and then 3. Let me write R here. It's NCR on your calculator, but in a problem like this, R and X are the same thing. They mean the same thing. Okay, let's go to 12. Okay. 12 says, based on a survey, when 1,009 consumers were asked if they are comfortable with drones delivering their purchases, 42% said yes. The probability of randomly selecting 30 of the 1,009 consumers and getting exactly 24 who are comfortable with the drones is represented as 0 plus. What does 0 plus indicate? Does 0 plus indicate that it is impossible to get exactly 24 consumers who are comfortable with drones? So this problem requires us to recall what are probabilities. What is probability of X? Probability of X is an area underneath the normal curve. So we've been working with the normal curve for a while now. So any P of X is just this area. This is what it represents. So P of X is equal to the area under this curve. Now here's the challenge, is that they've asked us for the area under a curve when X is exactly 24. So we would find 24 on this normal curve on the x-axis. Let's say it's over here. Here's 24. That forms a line under the curve. And for exactly 24, the question then becomes, what's the area of this line? And there's a problem here because you can't find an area of a line. A line has no area because it has no width. So yeah, it looks like it has a width because of the pencil, right? But technically this width here is infinitely small. This width is almost 0. It's approximately 0. So to do a problem like this, you can never do exactly 24. You'd have to do this. You'd have to say, actually I can use this picture here. You'd have to say, let's look at between 23.5 and 24.5. So that way I have a width of 1 or some small width. And we'll see this a lot in future sections where to do this formula, in the future we're going to use the normal curve to approximate that formula because that formula can break down with too big of numbers. We'll have to do this right here. Instead of using 24, we'll use just below it, 23.5, and we'll use just above it, 24.5. But you can still use that formula to get exactly 24. In fact, let's see how we'd set up that formula. In this one, they're selecting 30 people, so that's N. They're looking for 24 okay with drones, so that's X. Now, we can't actually do this problem because, actually we can. P is 0.42. I didn't know they gave us P. That's why I thought we couldn't. Therefore, Q is 0.58. And you could take these 4 numbers, plug it into this formula that we developed or wrote down. And so we'd have 30 factorial, 30 minus 24 factorial, 24 factorial, 0.42 to the 24, 0.58 to the 6, and you get a number. And in this problem, what they're saying is the number is so small that they're just going to call it 0 plus, which means it's just above 0. Just above 0. So a very, very small number, but not quite 0. So the answer here would be the probability B. The probability 0 plus indicates that the probability is very small, positive value. It indicates the event is possible, but very unlikely. So it's almost going to be very rare that you would sample 30 people and exactly on the nose 24 would say they're okay with it. And that concept will come up again. We'll do this concept enough where you'll get tired of me saying it, because we'll just drill it until we really get it. So if you don't quite get it yet, that's okay. Okay, 13 says determine whether the given procedure results in a binomial distribution or a distribution that can be treated as binomial. So we need the requirements for binomial. So let's write them down. Requirements for binomial distribution. One is that your procedure has fixed number of trials. So n is some constant. And I'll write down an example right next to this so we can see it, how it works. So the classic example for this is a coin toss. And so I can just say, well, let's let n be 100 times. So that means I'm going to flip the coin 100 times. But the whole point is it's fixed. I'm going to set that number 100, and that's exactly what I'm going to do. I'm not going to do any less than that, any more than that. 2, trials are independent. So one trial does not affect another. So if we think about a coin toss, if I flip tails the first time and then heads the second time and then heads again, these flips do not change my next flip. So this tail did not force me to get a head, and this head did not force me to get another head. So they don't, it doesn't matter what, in fact, they don't care. So this head, this third head doesn't care what the first two were. Okay. 3, each trial has 2 outcomes. And exactly 2 outcomes. And we're going to call those success, which we give the probability P to. And then we're going to say the other one is failure, which we give the probability Q to. So I just have to pick. I have to say, in my coin flip, I have to decide, well, do I care about getting heads or tails? So I'm going to say heads is considered a success, and therefore a tail is considered failure. And it's just a way for us to track the 2 different outcomes, success or failure. Then the last one, for probability of success, which we're calling little p, remains constant in all trials. So if we're flipping a coin and we're interested in getting heads, then P is 50%, because a coin is, if a fair coin is considered 50-50. 50% heads, 50% tails, and those do not change. So I can flip that coin 1,000 times, and my probability of a head is still 50%. It won't change throughout the experiment. Okay, so these are pretty simple, but in any kind of experiment, if we want to use the binomial distribution, we have to check these 4 conditions. So that's what they want us to do in 13. They want us to see if this problem meets these 4. So let's take a look. 7 different senators from the current U.S. Congress are randomly selected. So first off, 7, n is 7. It's constant, so they're not changing this number. So that would be requirement 1. So procedure 1, check. Procedure has fixed number of trials. Are randomly selected without replacement, and whether or not they've served over 2 terms is recorded. So trials are independent. One trial does not affect another. So 2. If they have 7 Congress people and they're randomly selecting 1 and asking that person, hey, have you served more than 2 terms? Without replacement, though, this is the problem. So notice in the first trial, there's 7 senators to pick from. In the second trial, now there's 6 to pick from. So that violates several. So this is going to violate 2 because these are no longer independent. My sample is shrinking. And 3, each trial has 2 outcomes. So you could maybe get this one. So whether or not you serve 2 terms, that only has 2 outcomes. Yes, I've served over 2 terms, or no. So 3 would be okay. Probability of success remains constant. So again, if I ask, my probability is going to change because this number n is changing each time. So this one violates a couple. So we would say, can we use binomial? No, because there are more than 2 mutually exclusive outcomes. No, that's not quite right. Because the trials of the experiment are not independent and the probability of success differs from trial to trial. That's exactly right. So we lose independence and we lose constant p. That one's kind of tricky. I wish we had a simpler one out the gate, but there it is. Okay, 14, and I just realized something. 14 requires a table to go with it. And I don't remember if I pasted that at the end of... Nancy, do you have your notes on you? You do, right? Do you have at the end like a table? Is that the entire class notes or just this chapter? Yeah, that's all. What's that? That's everything? Yeah. Flip to the far back, because at the very, very back, I pasted tables that we need for the course. Yeah, there you go. So there's like a Z table. Do you see anything that looks like this? So it's got kind of numbers laid out like this. Keep flipping. I'll see it. I'll recognize it when I see it. That's the last page. That's the last page? Okay, so I forgot to do that. It actually doesn't matter because so when you guys do this problem, there'll be a table that you can click on, and the table will look like this in the homework. And it's really, really simple. So all you have to do is find your number of trials, n. So it goes 2, 3, 4, 5, 6, etc. And then you just have to find the given p-value. So let's look at this problem. So they tell us in this problem that n is 4. And they want a probability of success p to be 80%. Use a binomial probability table to find the probability that the number of successes x is exactly 3. So they want us to find x equal 3. So here's how simple this will be when you do this on your homework. N is 4, p is 0.80. So you're going to go to n is 4, p is 0.80, and then you're just going to go, and then you're going to, so n is 4, but then x is 3. So you go to the n, so notice in n is 4, there's only 5 possibilities. X is 0, 1, 2, 3, or 4. They told us x was 3 in the problem. So we go to x is 3, p is 0.80, and we find the intersection of those two things, and it turns out to be 0.410. So the table should be pretty easy to read once you have it on your computer screen. And so you just look this up. So it's 41% chance that with 4 trials and a p of 80 that you get exactly 3 successes. Okay. And what that does is it allows you to skip that formula. So our formula, again, our formula is kind of complicated. It's all this stuff here, right? Well, those tables allow you to bypass this formula. Now, the drawback is the tables don't go very high. So, in fact, this table only goes to an n of 8, which is very small. Okay, and then let's look at 15. So 15 is also going to rely on that table. So it says, assume that random guesses are made for 4 multiple choice questions on a test with 2 choices for each question, so that there are n equals 4 trials, each with a probability of success correct given by p is 50. So n is 4, p is 0.50. Find the probability of no correct answers. That would be x equals 0. So those are only 3 things we need. So again, we would go to this table. N is 4. So again, we're in this region here. And then x is 0, so it's the first entry in the n is 4 block. And then p is 0.50, so we go to 0.50. And then just the intersection of those two things, the overall answer would be 0.062. So we would say 0.062. Okay, so 14 and 15 are pretty simple. They're just table lookups. 16 is more interesting because it's going to require us to use that equation. So a survey showed that 84% of adults need correction, eyeglasses, contact surgery, etc., for their eyesight. If 15 adults are randomly selected, find the probability that no more than 1 of them need correction for their eyesight. Is 1 a significantly low number of adults requiring eyesight correction? So let's identify our letters. We talked to 15 people, so n is 15. 84%, that's going to be p, 0.84, which means q, we should write this down right away, is 0.16, because those two add up to 1. Here's where this problem's a little tricky. Probably that no more than 1. So this right here means, what's the probability that x is less than or equal to 1? X being less than or equal to 1 has 2 possibilities. That's the probability that x equals 0 plus the probability that x equals 1. So we actually have to do our formula twice. One where x is 0 and one where x is 1. So the formula says, let's actually write it so that way we can see how to plug it in easier. N factorial, n minus x factorial, times p to the x times q to the n minus x. So when x is 0, this first case here, n, which was 15, we get 15 factorial, all over 15 minus 0 factorial times little p, which is 0.84, raised to the 0 times 0.16 raised to the 15 minus 0. So all I did was replace all these letters here with their corresponding number. All n's are 15. All x's in this problem are 0. Little p is 84. Little q is 16. And this one's kind of nice because 15 minus 0 is 15 factorial over 15 factorial. 0 factorial is 1. This is 1. So this first term, you just get 15 factorial over 15 factorial, which the whole thing is just 1. This number here, 84 to the 0, any number to the 0 power is also 1. So that just leaves your the final thing you have to punch in your calculator is just 0.16 raised to the 15th power. And if you do that, you will get 1.1529 times 10 to the minus 12th. Okay, then the second part of the problem says, what about p when x is 1? It's going to change this formula a little bit. 15 factorial over 15 minus 1 factorial, 1 factorial. 84 to the first, 0.16 to the 15 minus 1. So the only thing that changed in this formula is now all these x's became 1s. So 1 here, 1 here, 1 here, 1 here. And what you're going to get here is 15 factorial over 14 factorial. When you subtract 1 from 15 here. 1 factorial is also just 1, so we don't have to really worry about it. Times 84 to the first power is just 0.84. Times 0.16 to the 14th power. And if you do that, you will get 9.079 times 10 to the minus 11. Now the final step says you have to add these two together. So you're going to add these two numbers. And your final answer is going to be 9.1945 times 10 to the negative 11. Which this is a 9 with 10 zeros in front of it. And if we're going to round to 3 decimals, it's just 0.000. So this number is like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I mean, don't even write that down. That number is just really, really, really small. And when I round to 3, I'm just going to get the first 3 zeros. And if we think about this should make sense. If 84% of people need corrective I stuff, and we're looking at the probability of 0 or 1 of them, that's going to be a tremendously low probability out of 15 people. So, is 1 a significantly low number of adults requiring eyesight correction? Note that a small probability is 1 that is less than 0.05. Well, this is definitely less than 0.05. So the answer is yes, this is extremely low. This probability is very small. Now the easy part is writing these numbers into this formula. The hard part is getting the number right on your calculator. So you should try to practice this later on your calculator and make sure you can recreate my numbers here because that's the tricky thing. Okay, let's look at 17. Assume that the hybridization experiments are conducted with peas having the probability that for offspring there is a 0.25 probability that a pea has a green pod. Assume that the offspring peas are randomly selected in groups of 32. Complete parts A through C. So right away, we should write down NP and Q. So N is 32. We have 32 P's at a time. We're interested in the probability of green. So P, our success criteria, is 0.25 right here, which means Q is 0.75. Those two things add to 1. Now in this one, they want us to calculate the mean number of green P's. Well, this is pretty simple. Mean, which is mu, for binomial probabilities is just equal to N times P. So the number of things you have times the probability of success. So in this problem, we have 32 P's times 0.25 of them will be green. So 1/4 of 32, which would be 8. So out of 32 P's, we would expect 8 of them to be green. The standard deviation, which is sigma, is equal to the square root of N times P times Q. Well, notice we just did N times P, it was 8. So this would just be 8 times Q, which is 75%. And if you do that, you will get the square root of 6, which is 2.449. Rounded to one decimal place, we'll call it 2.4 P's. Okay, then part B says use our range rule of thumb to find out significantly low or significantly high. Well, we've seen this formula many times now. Sig low is mu minus 2 sigmas. So in this problem, it would be 8 minus 2 times 2.4. And if you do that, you get 3.1. I think you have to be careful in rounding this number. I think you have to use more of these digits than just 2.4. So use 2.45 here. This rounded to 2 decimals. For sig high, it's mu plus 2 sigmas. So it would be 8 plus 2 times 2.45. And if you do that, you will get 12.9. So we would be shocked if out of 32 P's we had fewer than 3.1 green ones, or we would be shocked if we had more than 12.9 green P's. Then the last part says, is the result of 2 P's with green pods a result that is significantly low? Well, again, on our number line, anything lower than 3.1 and anything higher than 12.9, so anything in this region is sig low, anything in this region is sig high. So if we had 2, that's about right here, that's clearly in the significantly low section. So the result is significantly low because 2 P's with green pods is less than that 3.1. Questions? Okay. 18 is the binomial distribution when we use replacement, without replacement. And we have a small population. So when you have a small population, there's a chance that you can lose independence. So we say these are not independent. And the formula becomes even nastier. So the binomial probability is already challenging. As you'll find when you try to do these problems on your calculator, you'll find that they're not easy to punch in and get the right answer. Well, this one's even worse. This one is just a plug and chug. So they give you A, B, X, N, and they tell you what those are. But it's just a little bit more work. I didn't realize how much work this one would be when I got it. It's not a ton of work, but it's high probability for mistake. So here's what I want you to do. I want you to skip this problem on your homework, and I will give you all credit for it. Okay, so don't even do it. Just go right past it. You'll get credit at the end. I will add in the number of points necessary to account for that problem for your final grade. So just don't do it. And I will never ask you a test question about it. And I'm highly confident you will never see that question or that problem in your professional career where you need to do this sort of math. Okay, so let's go to the last two, which are just kind of our vocab ones. So if calculations are time consuming and if a sample size is no more than 5% of the size of the population, the blank states to treat the selections as being independent, even if the selections are technically dependent. So this is called the 5% guideline for cumbersome calculations. And here's the whole key to it. So as long as you're not talking to more than 5% of your population, you can assume that those people are independent of the rest of the population because you haven't drawn a big enough sample. So if you talk to too many people, there's a chance you might start talking to family members or people who, go to the same places together. They mingle. You start to break down this independence that we needed for our requirement. But if you stay under 5%, you can just assume that they're independent. Okay, the last one. In the binomial probability formula, the variable x represents, probability of success in one trial, that's called P. Number of trials is called N. Number of successes is called X. The probability of X successes among N trials, that's P of X. So it's number of successes. Questions? Okay, that will complete section 5.